So, friends, by now you would have realized that the fundamentals of all the deformation process remain same. The parameters which we need to understand in all these are the same, like the strain rate and temperature, and according to that the flow stress of the material will change, and that we have discussed thoroughly in last several lectures. It is now time to move on to the next important fundamentals, which is to understand what will be the total load requirement, total power requirement or pressure requirement, total stress requirement when we are trying to do deformation process. In this process of trying to understand this mechanics, we will also be get to know some more process or some of these processes that we have discussed in little bit more detail, like we will see particularly wire drawing process and the rolling process and the extrusion process in a little bit greater depth. So, our next target is to understand mechanics. What we are trying to understand, like I said, are the load requirements, the force calculations, the stress calculations and so on. There are different ways or different techniques that have been developed, and I will list out some of those. One of them is uniform energy method, which is also called as lower bound, meaning whatever load stress requirements that you calculate using this method, that is the minimum that will be required, and you will see why it is the minimum. Then there is something called as slip line field, where you assume some particular place along which the shear is taking place, and according to that you calculate the stress requirements for the overall deformation. Slip line field, sorry. Then we have what is called as upper bound analysis. Though we will not prove, but as the name suggests, upper bound analysis puts the upper cap on that load requirement or the stress requirement. So, if you know upper bound stress or the stress calculation using this method, then you know that is the maximum load or stress or pressure or power requirements for that particular kind of deformation. And therefore, to be able to give a, you can say, to have a holistic view, what we will do is we will go with upper bound analysis, the uniform energy method, which is the lower bound, and the upper bound analysis. So, we will discuss these two in our course, so that you will know what is the lower bound and the upper bound. So, yeah, the actual values must lie somewhere in between, and of course, there are some more intricate and more accurate methods, but which require computational techniques. So, something like finite element analysis, where you can distribute the whole element in 2D arrays or 3D arrays and calculate the stress strain at each and every of these for each and every element of these, and then accordingly calculate the total load requirements. So, as the name suggests, this is more computational in nature, and the above three are analytical in nature. So, but the two that we are looking at are also analytical in nature. So, let us start with uniform energy method. Before I get to uniform energy method, there is one more thing in general that you must be aware of when we are discussing the different techniques, and it is that these techniques don't expect that when we are doing this analysis we are able to get all different kinds of information. We are only limited to calculating total load, stress and pressure, power requirements like this, but it does not, these analyses do not provide information on something like these. It does not tell you the mechanical properties of the material. For that you will have to understand the mechanical behavior, or you will have to take a full fledged course on mechanical behavior of material. It does not tell you what will be the maximum deformation. So, sometime you may see that the deformation should be 0.3, but it is not telling you if actually the material could be exposed to that kind of deformation. So, those things are beyond the purview of this analysis. Variation in frictional forces. So, there may be variation in the frictional forces, or sorry, not the frictional forces, but frictional effect. So, you will have to assume some kind of a frictional field, and accordingly you can calculate the total effect or the total load requirements, total or the overall change in the mechanics. But it will, this method will not tell you what kind of friction and frictional effect does exist, what are the different kinds of frictional variation that exist in that particular material or that particular process. So, you must be aware of the limitation. In some ways you can say these are the limitations. Do not expect everything to come out of this kind of mechanics analysis. This method can only give you the load requirements, stress requirements, and so on. So, now coming back to our what we were discussing, what we wanted to discuss, which is uniform energy method, or also called as lower bound. Why is it lower bound? By the name itself, you should have realized by now that what it is saying is that the ideal work needed to do the deformation is what is calculated using uniform energy method. So, this is in effect nothing but energy balance. I will explain in a little bit more. External work that is done for the process is equated with ideal work for deformation. Now, what is ideal work? Let us say you have a bar like this, and I am just for the sake of better visualization, I am dividing it into several grids. Now, let us say I want to deform it and make it thinner. So, when you make it thinner, it will also expand in one direction. So, let us assume it is 2-dimensional in nature, that is third dimension remains constant. So, after deformation, this is, so the 4 lines should remain 4 lines and the 2 lines should remain 2 lines, only they are closer and the vertical lines are now further apart. So, this is the deformation that I want. So, this would be ideal work. However, in reality what happens is not always ideal in nature, and what you may get is something like this. So, now what do you see? Each of the elements have more or less acquired the same shape that we desired, but at the individual level there is some additional amount of deformation, and whenever there is additional amount of deformation, it means additional work must have been carried out. So, there is some redundant work being done here. There is additional energy getting consumed in doing this additional deformation, which was not required. I do not want this additional deformation, I want only this much deformation. So, there is some additional redundant deformation which is not required, and that also implies that you need additional work or additional energy. that is one thing. Then there is also frictional work. Let us say that you put two dies on top and bottom to do the deformation. So, you are assuming that this layer would slide easily against the die on top of it to get the deformation like this, but it may not be the fact, it may not be what actually happens. In reality, what will happen is that the surface of the workpiece will have to work against a frictional force of the die, and therefore, there is again some additional work required. So, there are these two main additional work required which increase the total amount of work required. So, if you were to put it, this is your Wi, which is ideal work, this is Wr redundant work, and this is Wf frictional work, and the actual work is the sum of all these three. So, you see we wanted only this much, but we have to do additional work, and therefore, the total energy requirement, work requirement increases, and this efficiency of the ratio of ideal work to actual work, that is called efficiency W ideal by W actual, and it will be less than 1, because actual work requires more energy or more work than ideal work. Therefore, Wi by Wa will always be less than 1, or I should say less than equal to 1. When will it be equal to 1? When Wr and Wf are 0. So, there is no redundant work, no frictional work. In that case, our ideal work would be same as actual work. So, this is important concept which will be utilized to calculate the stress requirements for uniform energy method. So, we are only devoting to the work ideal, that is how much would be the energy or the force requirement if nothing else was being done, if no redundant work was being done, if no frictional work was being done. So, let us look at one example, not example, but let us formulate a simple equation for this ideal work. Now, W ideal, as we said, it can be easily given by just the amount of work that is required for deformation. So, if the flow stress of the material is sigma, the actual deformation required is d epsilon bar, and you have to change the strain from 0 to epsilon bar. Then work, ideal work, which is work per unit volume. So, you should be aware of the unit, it is not the total work, but work per unit volume. So, the ideal work is nothing but integration of flow stress, equivalent flow stress times equivalent d epsilon integrated over the whole strain range. Now, assuming power law behavior, what is power law behavior? It was this kind of behavior. So, assuming that our material follows this kind of flow behavior. So, the flow stress is given by this equation where K and N are constant. We have already seen those equations earlier. Then what you need to do is just put it in here, and you would be able to show that ideal work is nothing but, it will boil down to this equation. Ideal work per unit volume. Okay, so, keep that unit in your mind. This is ideal work per unit volume, assuming a power law behavior can be given by this, where let us say this is the total strain that was to be given to the material, or for that whatever element that we are talking about. In that element, if this is the total strain that was to be given, so that work per unit volume in that element, in that component, in whatever unit we are looking at. This equation gives you the total work done per unit volume. And this is not only limited to power law behavior. You could have a stress behavior, flow stress behavior described by something like this. And in that case, what you would get, so you will have to multiply, or you will have to integrate sigma d epsilon over the range 0 to epsilon bar, and what you get is so the only point I am trying to make here is that do not take this equation as you can say hard and fast rule. It depends on what is the flow behavior. The fundamental equation is this: you have to integrate flow stress times d epsilon bar, and if the flow stress was given by this, you will come to the work per unit volume equation something like this. So, now it is time to solve a simple equation. Every time we have a equation, we move on to we try to solve a equation or solve an example based on that. So, let us say a material strain hardening behavior is given by 250 epsilon bar to the power 0.25. So, K is 250 megapascal, as you would see I am writing the unit over here, and N is 0.25. So, this is the flow stress behavior that you are given, and it is said that in wire drawing operation is where you thin down the wire by doing deformation on it. We will again draw the details of it in a moment, in another example that will come very quickly, come to it very soon. But for now, it is suffice to say that wire drawing operation is where you take a wire, thick wire, and the process is such that it reduces the diameter of the wire. So, in this case, the wire, when you are doing the wire drawing operation, the diameter was reduced from 12.7 millimeter to 11.5 millimeter. Now, you remember, if you, what you have to do is calculate work ideal, that is total work per unit volume. The first thing that you may think of is to calculate the strain, or basically what you would think is that Wi is given over there for power law behavior. So, we know K, we know N, and only thing that we need to calculate is strain. True, that much is right. However, how do you calculate strain? Again, this is something you have to be always careful about. We have to calculate the effective strain, and effective strain, if you remember, for wire drawing operation is equal to epsilon 1, which is what? Which is equal to ln A final by A naught. Sorry, it is A naught by A final. Now, A naught is what, or A is given by pi d square. So, this comes out to pi d naught square by pi df square, or you would see it comes down to 2 times ln d naught by df. The point I am going through each and every step is again that just because I have given in the question, in the problem, d naught and df, do not assume that epsilon 1 will become ln d naught by df. If you see the way if you go by the first principles, you get that epsilon bar is equal to 2 times ln of d naught by df. So, now you put in the values over here and you would see that it comes out to 0.199, and we will put the same values over here and you would see so it will come down to 26.5 megajoule per meter cube. So, that is the amount of work that is being done when you do a simple wire drawing operation on a material with this kind of flow behavior. So, this is the way to calculate the work ideal and to calculate the strain. So, you have to, again like I said, you have to be always careful in how you calculate strains. Next, what we will look at is to relate in extrusion or in wire drawing process the pressure that is required for extrusion or the stress that is required for wire drawing to the total or the ideal work that is required, that is needed. So, let me start with extrusion. So, let us say this is our die, and this is the material that is being pushed through. So, you are applying some pressure PE, PE meaning P extrusion. So, extrusion pressure. So, extrusion pressure is what? A force divided by the area. So, let us say the area over here is A naught. Now, let us consider a small element over here. The length of this small element is delta L. How much force is being applied on this small element? It is Fe. What is the area of this small element? It is circular, let us assume that it is circular in nature. So, the area of this small element is cross sectional area is A naught, and if you now consider that you have moved from this region to this region. So, this is the actual work that you would have done. So, let us say whatever is the PE or Fe, that is the we are not relating it with any inherent property or inherent behavior. We are just saying that there is, from somewhere there is some pressure or force that is being applied, and when you are applying that force you are doing some work. What is that work? You are moving this is very infinitesimally small element from this point to this point. So, there is work done. Now, if I want to calculate work done per unit volume, and this will be the actual work because I am relating it to the actual pressure or force required. So, the work done per unit volume will be total work by volume. Work is what? Force Fe times delta L, and volume is what? This is the area, cross sectional area, and this total work has been done in this overall volume. So, A times delta L, or work actual is nothing but Fe by A. Actually, this is A naught. So, this is A naught, and Fe by A naught is, we said it is PE. So, this is P extrusion. So, the actual work per unit volume is equal to the actual pressure that is being applied. Now, we know that WA is greater than equal to WI, therefore, PE is greater than equal to integral sigma bar d epsilon bar 0 to epsilon. So, now we are using this relation, we have derived a relation between PE and sigma bar, or the basically the ideal work. We already know that W actual should be greater than W ideal, and here W actual is nothing but the actual pressure that you are applying, and this is your ideal work. So, P E has to be greater than this, or in other words you could have said P E is greater than, or actually is equal to 1 over eta. Eta is the efficiency, because in terms of ideal work we are, if we want to put, then W ideal by eta is the actual work, which is equal to P E. So, we can write it like this. So, this is a very again important result. What are the different possibilities? The different possibilities are eta is equal to 1, meaning we are saying that it is a ideal work, that is all, there is no redundant work, there is no friction work. In that case, P E is equal to 0 to epsilon bar sigma bar d epsilon bar in case of ideal work, or meaning no loss in WR or WF. So, no loss during redundant work or frictional work, then in that case we get eta equal to 1, and therefore, P E or the extrusion pressure is nothing but integral of this quantity. It is a very useful relation that you will see later on. In a very similar vein, I would want you to do the similar kind of derivation or analysis for the wire drawing operation. So, let us say this is my initial diameter d naught, this is the d final, and this is sigma d, which is associated with F d, and let us say this is d f. So, there is also area A f A naught. So, do a similar analysis to find the relation between sigma d and work actual. So, I will leave you with this thought. We will actually do it in the next class, but I would hope that you give it a try, because it will give you a good feel of the numbers or the way that we are getting to this equation, and it will also be helpful in solving some further problems. So, thank you, and try to solve this problem. Thanks.